Hello, and welcome to the suboptimal lecture series. I'm going to give um, some version of which I would give in the good old days of organic chemistry when you sat in a lecture hall. These films will be 20 to 25 minutes long, and they'll sequentially go through the first four chapters and a discussion of IR. Um, if I get to above, 11 hours, which is the four lectures that you would hear before the first exam, I'll stop there, and that's what the first exam will be. Hopefully you'll hear all this well in the first meeting we have on the 18th of May. So let's jump right into it. I'm going to teach this course using a combination of the slides provided that mimic the textbook and some slides that I've created. And I'll stop at some logical junctions when I stop these videos. Be aware that while I'm doing the first four chapters, I have chosen to do things in a slightly different order in some cases. For instance, I decided that you should hear about molecular orbital theory and about hybrid orbitals before you hear about resonance, which relies on it. The text inexplicably does it in the other order. So, but I'm going to follow more or less the slideshow that you have access to on Brightspace. So, as I said, let's jump right into it. So, we are involved in carbon chemistry, organic chemistry, because it's the chemistry of living things, or at least that's how it got its name. In the 1800s, we realized that carbon didn't have to be derived from living materials. And in the modern world, gosh, we have everything. We have the chemistry of carbon involves any number of things, including all the molecules you see here, like coal and carbon fiber, small molecules. Everything in your body is effectively a carbon-based thing. Modern polymers and plastics, pharmaceuticals, all kinds of synthetic materials, obviously fossil fuels. We're all obsessed, rightfully so, with the issues around fossil fuels, food and nutrition, genetics. I list Kary Mullis, who developed the polymerase chain reaction test as part of a modern forensics. So this is more or less background, what I just said. The discovery of urea, a molecule we'll confront at some point, expanded our definition of organic chemistry, carbon chemistry, to include molecules not derived from life, and much of synthetic chemistry is not based on plants, obviously, but often it's trying to mimic the chemicals in plants. So that organic idea is sort of revolving back to being true. I think it's kind of funny, the different definitions of the word organic. Organic farmer doesn't use pesticides, and an organic chemist says, but pesticides are organic molecules. So, what can you do? So, we're going to start with things but we're going to remind you of them. For instance, that there are shells of electrons. You have down below you the first, I don't know how many elements of the periodic table, and you know that there are subshells in S and P and D, and that within these shells, there are orbitals of 2 electrons. So that S has 1 orbital, which can contain 2 electrons. P has 3 orbitals, orthogonal orbitals in the x direction, the y direction, and the z direction. And D has 5, though we'll rarely confront D orbitals in this course. And then, of course, noble gases are those elements that have full shells. And effectively, I've always found it incorrect to call them 8 electrons. They really have none, right? So a couple of terms that unfortunately I want you to know and be aware. Organic chemistry features a lot of memorization, but I would like you to know, for instance, Aufbau's principle, which you know, electrons fill from a ground state from 1s to 2s to 2p to 3s and then 3p and so on, 4s before 3d. You can see it on the periodic table. It's a real cheat sheet. A couple of other ideas that I want you to know, and you have to know. For instance, the Pauli exclusion principle, which says that these 2 electrons are precessing with a spin, and these are conceits. We know that particles as small as electrons are as much waves as particles, but we can say that they spin, and that they spin necessarily in opposite directions. We always indicate that with half arrows up and half arrows down. And these are therefore opposites and paired. And one more thing to know, and this is very important, but you probably know it, and that is Hund's rule, which is what I was always told is the seats on a bus rule, which is if you get on a bus and there are 2 people on the bus, it is weird if you sit down next to one of those 2 people, right? Because half-filled seats are more comfortable for everyone. So degenerate orbitals, and degenerate here means of the same level. Degenerate orbitals, like the 3 2p orbitals, will half fill before one double fill. So you won't see 2 electrons in the px orbital and none in the p or y or pz, right? So they half fill before they double fill. So you get 3 half-filled orbitals, and then you double fill them to make 6. So we're going to start with things. I know this is slightly out of order, but I want to mention that we won't talk, obviously, about ionic bonding much. We'll reference it in some cases, molecules you think of as ionic, like aluminum chloride or aluminum or magnesium even, have some covalent character and play roles. If you're taking 252, you'll see this in action. We'll see it in action in this lecture course. But ionic bonding generally involves 2 atoms or 2 ions that feature the transfer of electrons from the cation to the anion, typically from a metal to a non-metal, but not necessarily a metal. It could be a protonated ammonia called ammonium, NH4+, but a cation and an anion, the electronegativity differences are going to be greater than 2. Remember that Linus Pauling's 4.0 scale sets out the electronegativity. More on that in a second. We call these particles electrostatic, static meaning not moving. An ionic species doesn't conduct electricity because no charged particles move, and obviously the movement of charged particles, and especially electrons, of course, is electricity. So that is, there it is, Pauling's table. I'd like to believe, though I have never read this proof, that Pauling loved to teach. He was a teacher as well as an extraordinary scientist. He won 2 Nobel Prizes and almost got the third for discerning the structure of DNA. In fact, in Watson's and Crick's paper, in the first sentence, they cite Linus Pauling as, almost got it, but he got it. So he was a teacher as well. And I like to think that he made this relativistic scale up as a 4.0, meaning that fluorine gets a 4.0, an A star, whereas, cesium gets an F. But anyway, this is not a table you would ever have to memorize. And in fact, we'll largely be concerned with about 5 or 6 elements in it. Organic chemistry, especially first semester organic chemistry, is really about 4 elements. So I don't think it's a terrible idea that that carbon is 2.5 and oxygen is 3.5. Nitrogen is 3.0. That's pretty easy to remember. 2.5, 3, 3.5. And that hydrogen is slightly less than carbon. So it's not a polar bond. It's considered a nonpolar bond, but there is some electronegativity difference between carbon and hydrogen. And still, because it's largely a nonpolar bond, CH bonds are extraordinarily strong and stable. It's polar bonds where the electrons can break most easily and form cations and anions. So here is that codified. Polar covalent bonds will sever more easily. Their energy of breaking those, the bond energy, is lower. We won't spend any real time talking about mu, the dipole moments, but it's worth knowing that that kind of thing exists. Here's some notation methods that we'll see frequently. You should know that that delta indicates the word partial. I'm sure you know this from general chemistry. So that in the far left image you see there's a partial positive charge on A, a partial negative charge on B. That means the electrons, which are as much waves as particles, are more frequently towards B. So it has a partial negative charge. We can indicate this with the arrow with a plus sign on the back. You'll see that often as well. These are as opposed to, for instance, in sodium chloride, where Na has lost an electron and Cl has gained an electron, and those are called formal charges. So have in your head those ideas, partial charges and formal charges. They refer to covalent bonds and ionic bonds. So here we are with some famous electronegativities. I think you can round to 2 significant figures and refer to oxygen as 3.5, nitrogen as 3.0, carbon is 2.5, and hydrogen is 2.2. If you know those 4, you're going to be in a good place for at least 251, the first semester organic chemistry course. And here I state the ones that I think you should know, and we could perhaps add phosphorus. The closer you are to fluorine, which is the 4.0 element, the more electronegative you are. So, of course, chlorine is more electronegative than bromine, and which is more electronegative than iodine. But I make a point down below there of that methyl magnesium bromide. And you think, well, magnesium is a metal. Of course, it's ionic. And I'm here to tell you that while it's a very polar bond, the difference in electronegativities is 1.2 between carbon and magnesium. It's actually partially covalent. And we're going to take advantage of that, especially in the lab, where we'll use magnesium bromide, methyl magnesium bromide, I think specifically, to do some chemistry. So anyway, there are our discussion of ionic bonding. Be aware that the text often has electrostatic mapping, and it kind of makes sense. Red is high energy and electronegativity, whereas blue is low energy, low electronegativity. We're going to talk eventually about the idea that polar bonds don't necessarily make polar molecules. In fact, in 3 of the 4 cases here, there are polar bonds and nonpolar molecules, in that the dipole moments are mathematically canceled. We'll talk about how methane's a tetrahedron, and so all the hydrogens are, even if they're being electropositive, which is a term they don't typically use, but we should know. Electropositive means the opposite of electronegative, having less electron density. They're all electropositive, but in some they cancel each other out because they're equal and opposite, just as that BH3 features 3 electronegative hydrogens all canceling each other out in a planar triangular geometry. And yes, I know you enjoyed geometry and shape in Gen Chem, and it's going to play a huge role here. So for instance, the difference between carbon dioxide and water is not that one is, in both cases, we have a central atom with 2 atoms outside it, but because one is linear, carbon dioxide, and one is a tetrahedron with 2 lone pairs, their chemistry is obviously dramatically different. The boiling points of carbon dioxide and water differ by 280 degrees Celsius. One boils at minus 180, one boils obviously at 100. I think you know that the anion, the non-metal component of an ionic bond, can be polyatomic, in which case all the atoms in the anion are covalent and share electrons, but can have an overall positive charge. And we know so many of these sulfates and bromates and acetates and carbonates and all kinds of things, and hydroxides and methoxides. So anyway, I think that's easy. So let's start with simple ideas you can easily grasp and own already. And I apologize for being patronizing here, but why does hydrogen form a covalent bond? Well, the answer is that hydrogen has 1 half-filled orbital, right? It has a 1s orbital with 1 electron in it. And by sharing those electrons, it fills that orbital. Filled orbitals infinitely preferable to half-filled orbitals. And so what happens with hydrogen? With hydrogen, they come towards each other to share those electrons to fill that orbital. But if they get too close, their nuclei repel, and there is some bond length at which the energy is minimized, where the most advantageous situation where the orbitals are filled, but the nuclei are as far apart as possible. We call that bond length, right? We can establish bond length, and it's an intuitive idea. You don't want the nuclei too far towards each other, but you want orbitals filled so that no half-filled orbitals exist in a molecule. And so we can use this idea to find bond lengths, and bonds have lengths on the orders of, picometers and nanometers, and we'll see that mathematics. You might even memorize the difference between a CH bond and an alkane, a CH bond and an alkene, or a CH bond and an alkyne, and in fact, a CC bond that single, a double bond of CC, and a triple bond of CC. These are eventually good numbers to know. I know it. The other idea is, how strong is that bond? So at that energy well, where the bond length is perfect, the bond strength is maximum, which is intuitive again. So here's what I was saying, and we'll discover why this is true when we talk about molecular orbital theory. But there's some really fascinating things here, and I think if nothing else, you should focus on the top line here, because this is a carbon chorus and lots of CC bonds will exist. If you have a single bond between two atoms of carbon, the energy of a single bond, and we'll do this in kilojoules only for this purpose, is pretty high. But if you add a second bond, intuitively, you know that two bonds between it, two ropes, makes the energy greater, although not doubled, nearly doubled, but certainly not doubled. That second bond, that pi bond, we'll say eventually, that second bond is weaker than the first, and the third bond, even weaker. You see that 339 as a single bond becomes 812 as a triple bond. The other thing I want you to notice is that as you get more and more rubber bands between them, the bands pull closer, so that you have, 0.154 nanometers of bond length, 154 picometers, 10 to the minus 12, of bond length for a single bond. But as the bond gets to be a double or triple bond, it goes from 155 to 135 to 120. So that a triple bond has lots of electron density, and we'll see eventually, therefore, very electronegative, pulls electrons even from the peripheries towards itself, and the bond gets shorter and shorter. I'm going to ask you on the first test about this. What happens to bond length? What happens to bond strength as you go from single to double to triple bonds? So you've been asked in any number of occasions to write Lewis structures, which require that atoms obey the octet rule. We're certainly going to dive into this in great detail in the next, video or two. But here's the octet rule, spelled strangely, electron.s1. So you can see that I'm making these slides up, and hopefully there won't be too many errors. But you'll notice that in each case, octets are obeyed, except for hydrogen, which needs 2 to be a noble gas-like configuration. We can also describe 2 electrons. Be aware, a line in covalent chemistry represents 2 electrons. So in that methane, CH4, you can draw it as 2 dots or a single line. But you should not forget that a line in covalent chemistry represents 2 electrons. And unfortunately, in the vast number of things I'll need you to memorize, is that in the lowest energy state, in the most typical configurations, carbon makes 4 bonds and has a neutral charge. You should know that nitrogen with 5 outer shell electrons can make 3 half-filled orbitals, right? Because of Hund's rule, half fills 3 orbitals and adds 1 more. Therefore, it has 1 filled p orbital and 2 and half-filled 3 others. We'll get to that. But therefore, it makes 3 bonds in 1 lone pair. Oxygen makes 2 bonds and has 2 lone pairs. And of course, halogens, 3 lone pairs and 1 bond. You should have in your arsenal how many bonds in the lone pairs these 4 critical atoms hydrogen, oxygen, nitrogen, carbon can make. But of course, we know that anything that can happen will. Hydrogen can make one bond, so that's the only example of what it can do. Carbon can make 4 bonds, and that versatility, although 2 double bonds will never appear in this course, even in the second semester of this course, it's just an unlikely configuration. But for single bonds, a double bond, a triple bond, those are all going to play huge roles in this course. Nitrogen can form 3 bonds, or 2 and 1, or 3. And if that triple bond is combined with the carbon, we call it a cyano. All of these are motifs that we're going to need to know the names of. Oxygen obviously could form 2 bonds, either from 2 single or 1 double bond, etc. So here's the trick I would like you to know. And I guess we've gotten to about 25 minutes. And so I'm going to finish this first lecture with this discussion of how you assign formal charges to different atoms. So let's say, sorry, well, my whiteboard's not working for me. So let's say you have carbon, and here's the trick you always want to know. If you want to know what formal charge an atom has, take the outer shell electrons, carbon has 4, and you subtract each, sorry, I have a pen for this, but it's not working, each lone pair electron and each bond. So, and this is valuable. So for instance, if I have carbon with 4 bonds, that's 4 outer shell electrons minus 0 lone pairs and 4 bonds. 0 plus 4. And so that's a neutral molecule. As you know, methane is non-charged. But let's say I have carbon with 3 bonds and no lone pairs. Well, now I know carbon has 4 outer shell electrons, and it's got 0 lone pairs, and it's making 3 bonds, and 4 minus 3 is plus 1. So the charge on that carbon is plus 1, right? However, if I have carbon like that, well, that's carbon's always had 4 outer shell electrons. It's got 2 lone pair electrons, and it's got 3 bonds. 4 minus 5 is minus 1. So what I'll finish with is this idea that you will eventually get used to the charge on different atoms and how that works. So for instance, here's nitrogen. And this is an extraordinary situation. So clearly, for instance, ammonia, that a proton was peeled off. Well, here's nitrogen. It makes 5. It has 5 outer shell electrons. It's got, let's see, 4 outer shell lone pair electrons. And it's got 2 bonds. And 4 minus 6 is minus 1. So the charge on this molecule, this amide, is minus 1. Anyway, I'll start the next video with this idea. But anyway, thanks for putting up with this motif for teaching. I would rather be in your presence, of course, but hopefully this will prove valuable. So I will see you soon for video 2, which will pick up with this idea of assigning formal charges.